instead of the front one. Okay. Sorry, is it?
Is that door open? We can use it because
I.
over there you need to log or something.
Ah.
Maybe they can change the line in.
Yeah, let one line.
Let's one line in 3.
Yes. I don't know if decide. Yeah, but it. Okay, I let you negotiate, solve this in the back. Okay, Joseph, the floor is yours.
All right, can you hear me? Let's see, can you hear me? How's that? Yeah, okay. All right, so today's my third lecture, and I'm going to start with a little bit of a review of the things I talked about the last 2 lectures, and then I'll talk about interactions today at the kind of heart of the discussion. But interactions in an optical lattice is a complicated business. It's really the subject of condensed matter physics. And once I kind of bring you from atoms and lattices all the way up to the model that is the starting point for a lot of condensed matter theory, I'm going to kind of stop there and hand the baton off to your condensed matter lecturer, maybe at home. Okay. So that's the plan. We're going to review a little bit, talk about models for interaction, and I'll try to bring this back to scattering of block waves, which is a perturbative problem you can understand, and then show you some data from quantum gas microscopes. Okay, so what we talked about on Friday, the first lecture, was how to solve the band structure of an atom in a periodic potential. And what we found was that because of Bragg scattering, the gaps opened up at the edge and between multiple bands in the lattice. And so this fractured what was a continuous set of energies in free space into these bands. And now, for a lot of the rest of the lecture, we'll just work within one of those bands, assuming that the connections between them are weak. The eigenstates, whose energies are shown here, are the block states. And the block states are, oh yeah, we have a zoom delay here. Okay. The block states are delocalized. So the wave functions exist across every lattice site. They extend for all space in an infinite lattice. And you can write them in terms of a plane wave-like phase factor characterized by Q, the quasi-momentum, times a periodic function, U. And so we talked about how to solve that. And we talked about some examples. So block states, for instance, in the lowest band have on site of each lattice a kind of single bump. And the next band, the first band, there's going to be a node, and the second band, there are 2 nodes. And I'm going to talk about where this structure comes from today in the limit of deep optical lattices. And then on top of this structure, there's a phase factor given by the quasi-momentum, and that looks something like this, where for low quasi-momentum, the phase evolves very slowly, and for high quasi-momentum, the phase changes faster and faster from site to site, and the fastest possible phase pattern you can have is that you go from 0 to pi to your neighboring site. Anything faster and you're going to go slower. In other words, if I go 0 to 2 pi, I've just gone to 0 again. Okay, so those are the block states. And then the next thing we talked about, which was in the second lecture, is how to localize atoms in a single site. And for that, we talked about these things called Wannier states. The Wannier states could not be infinitely narrow, because to be infinitely narrow, you would need all momenta. But instead, for the momenta available of a single band, we could do pretty well. So here is a localized site that now exists, a localized wave function that now exists primarily on one site with a little bit of extension to its neighbors. And as I get the lattice deeper and deeper, it gets narrower and narrower. But the fact that there is a little bit of wave function going from where I tried to localize and where a neighbor would be is responsible for tunneling. So once I try to put a particle on one site, it can still tunnel by quantum mechanical motion from one site to the other. And so we talked about how to calculate those kind of tunneling matrices. But let me just emphasize that these are conjugate perspectives. One of them, block states, which are the eigenstates, they're extended over all space, but they're at a well-defined quasi-momentum, whereas Wannier states are at a single site, but then require all of the quasi-momenta in the band. So the way we found this is we summed over all of these. And you go the other way as well. The way you find a block state is you sum over all the localized Wannier states, giving them the right phase to reconstruct that extended wave function again. Okay, one thing I didn't tell you about that I want to tell you now is, what if I take the Fourier transform of the Wannier state? So I had a single thing on a single lattice site, and I want to know what its momentum components are. Not its quasi-momentum components, but its real momentum components. And if I do that for a single, let's say, well here, this thing looks kind of like a bump. You Fourier transform a Gaussian, you get a Gaussian. But if I have, say, a first excited state and I Fourier transform that, I get something that looks like now a Hermite polynomial in momentum space. The block state at a particular quasi-momentum is drawing its momenta from a comb of possible values of the Wannier state. The reason that makes sense is that, remember, the Wannier state is the sum over all the block states. So I take all the possible combs and I add them on top of each other and I get a continuous function, and that's the momentum distribution of this thing. Okay, so this, because it's a wave function which is a sum of all block states, gives you a Fourier transform, which is the sum of all Fourier transforms of block states. Okay. All right. So today I'm going to start the lecture by discussing how to go deeper and deeper into the lattice and confining more and more onto a single site. And I talked about how once you have a deeper lattice, then you're dominated by a nearest neighbor coupling here, okay? Nearest neighbor tunneling. It becomes much faster than 2 sites or 3 sites away at fairly reasonable lattice depths like 10 recoils. And so in that limit, where we only use that nearest neighbor, we call this a tight binding approximation, and all the Hamiltonians and dispersion relations become very simple. Okay. So now let's talk about deep optical lattices. I've already kind of alluded to this, but if we start to make the lattice deeper and deeper, then the band structure, which used to have this nice kind of profile of a free particle plus some Bragg scattering, the Bragg scattering gets stronger and stronger, and so the gap gets bigger and bigger. And so does the next gap. This gap here, as I get deeper and deeper, becomes larger and larger. And those two gaps kind of squeeze the dispersion relation into nothingness. So what used to have a nice curve here becomes a flat line. And as I go to even deeper, here's 600 recoil, you can see that what used to be band structure with some kind of curvature just becomes a flat line. So these are called flat bands. And in this limit where these bands become very flat, if I now construct the Wannier function of a single site, then it starts to look like a harmonic oscillator. So shown here are the 0 band, the first band, and the second band Wannier function constructed in just the way I told you, integrating over block functions, and then comparing to them in dashed is what the harmonic oscillator would look like. And you can see that the overlap is pretty good, right? It's not perfect as you go higher and higher, but certainly for the ground state, it's great. And so this is a really nice way to approximate the probability density on a single site for a deep lattice. And let me talk about that for a little bit more detail. So first of all, why should that be so? Well, the reason you might expect something like that is our potential let's see here. There we go. The potential we're talking about is V lattice times sine squared of KL x. And a sine is something I can expand, so this looks something like VL times KL squared x squared plus VL times, oh, let's see, if I know my Taylor expansion, it's minus 1/3 VL, and the next order is KL to the 4th, x to the 4th, plus, etc. Okay, so this here is a quadratic confining potential. And so this looks like a harmonic oscillator. The harmonic oscillator potential would be 1/2 m omega squared x squared. To make those two match, I need to write down this harmonic frequency, which is something like the square root of 2VL KL squared over m. And if I look at this for a moment, that's the same thing as the geometric mean of the lattice depth and the recoil energy. And remember, the recoil energy is a photon recoil momentum. An atom with a momentum of a photon recoil has a recoil energy of kinetic energy. So the geometric mean between the lattice depth and a recoil energy gives you this, if I put it in the right units. Yes. Okay. So you can see that the leading order term of a sine squared potential is going to be a harmonic. And that makes a lot of sense so long as we're strongly confined. So if I have a lattice potential and I'm approximating this as some kind of parabola, then things are going to be fine if my atomic potential is, my atomic distribution is like this. That seems great. But if my atomic distribution is broad, then it doesn't seem so great, right? So for this thing to be valid as an approximation, I need to be sitting in the middle of the potential. And I know how to write down the self-consistency because if I have a simple harmonic oscillator, I know the solution. The ground state is just, e to the minus the n equals 0, okay, is a Hermite polynomial at n equals 0 as a function of x. And that looks something like a constant times e to the minus x squared over 2a harmonic oscillator squared, where this oscillator length is what? It's square root of h bar over m omega naught. And if I plug in this value up here that we just found for the harmonic oscillator frequency, then you can just write down that this is a lattice times 1 over pi to the lattice depth to the 1/4, okay? And S is just the lattice depth in recoil units. Right, so, okay, so this is the size of the harmonic oscillator wave function. And for this harmonic oscillator approximation to be valid, then I need the harmonic oscillator, this A harmonic oscillator to be much less than the lattice spacing itself. Did you have a question? Oh, sorry. Yeah. So, so the validity is then or the self-consistency is that a harmonic oscillator has to be much less than the lattice spacing. So this is the lattice spacing, and this is the harmonic oscillator. And if I just look at this equation here, it means that s to the 1/4 has to be much greater than 1. Okay, so this means that lattices need to be deep. Does that make sense? Okay, so that's why this kind of thing works, and you can compare, for instance, to if I just show you the harmonic oscillator function at the lattice depth is equal to 1 recoil, it's not so great. But as I get to 5 and 20, it's already great. It seems to work better than it should, because I just said that s to the 1/4 has to be much greater than 1, which maybe there's a factor of pi there that helped us, but okay. And another thing you can do is compare, as a fidelity, the harmonic oscillator wave function and the Wannier function, which is what I'm plotting here. And if you look at this comparison, things look quickly very good for the ground state, and it takes a little bit longer for a deeper lattice for the wave function to be at the right level for the first band. But still, for deep lattices, this starts to be a very good approximation. Okay. So what's this good for? So first of all, it's good to just have a nice analytic expression for the on-site density distribution in a lattice. But there's also something else which is really nice you could do with this, which is you can make low-dimensional clouds. Okay, so the situation I've been talking about so far is an optical lattice, and if I make 3 of those and I put them together, then I have some kind of 3-dimensional optical lattice here. But what if I just turn off one pair of laser beams, make a lattice in the other 2 directions, and then I go to this really deep harmonic oscillator limit? Okay. Then for each of these clouds, for every one of these sites, it'll look like a harmonic oscillator confining potential in, let's say, if I label this, the y and the z direction. I guess I should label y, x, z for a right-handed coordinate system. And so if I'm looking in the y or the z direction, I have some kind of simple harmonic oscillator potential in this deep lattice. And that's quantized with some kind of deep harmonic oscillator if I crank up the lattice. But in the other direction, in this z direction, I can have just a free or maybe weakly harmonically trapped cloud. Okay? And so atoms could, on the one hand, have the freedom to move in the z direction, but not have the freedom to move in the y. Oh, I'm sorry, I mislabeled. This is supposed to be x. Yeah. So in this free direction, then atoms can move along like they're living in a tube or in a one-dimensional space, but in the other directions, the lattice confines them from going very far. In fact, once their energy is much less than this first gap between the lowest band and the first band, you can just freeze out all of the motion in that direction, and now you have a quasi-one-dimensional system. So people have made tremendous use of this trick. Whenever you read an optical lattice or a cold atoms paper about one-dimensional physics, they're almost always using an optical lattice to make actually a whole array of these one-dimensional systems, and then studying them as copies of each other, a whole bunch of 1D things, okay? And you can do the same to make a whole bunch of 2D systems as well. If I left on, let's say, just this, but turned off this, then in the XY plane, I could be free to move like a 2D electron gas, but then completely gapped out of any freedom to move perpendicular to that plane. Okay, so then I form an array of two-dimensional systems. Also, a really great trick. We use it in my lab all the time. If we want to do 1D physics, we just turn off a laser beam. If we want to do 2D physics, we turn off 2 laser beams, right? So, yeah. So this is one limit. And so the perpendicular confining potential is always modeled as a harmonic oscillator. And the reason it's discussed as a harmonic oscillator is the math we've just gone through, that, you know, in this deep lattice limit, the on-site, the ground band on-site wave function for that lowest band is a harmonic oscillator.
Sorry. What's holding the atoms in the direction that's not the one from the lattice? Like in this, you have this one-dimensional system, and it's held like with a magnetic optical trap, or why is it?
No, it's, I guess you would just call it a quantum wire or something, or a quasi one-dimensional system.
Yes, but they doesn't escape in that direction. That's what I am asking. Why don't you lose the?
Oh, why?
Yeah, in that direction.
Because we intentionally turned off the laser.
Oh yeah, you know, but you have this stretched cloud.
Yeah.
And you are having this two-dimensional system in two directions. You have this discretized thing, and the other direction you don't.
Right.
I don't understand why they still are there. Like, what's holding them?
Ah, I see.
Sorry.
So you're saying, why don't they just go off it to infinity and leave? Yeah. Okay, so you need some confining potential in that direction. Indeed, you're right.
Okay.
There needs to be something left over. So one reason there is often a confining potential is that the optical lattice, which makes the standing wave potential, is itself an attractive potential.
Mm-hmm.
So you're making a potential where every time there's a maximum, so the intensity versus, let's say, the Z direction here is a red detuned laser beam. And so when the intensity is maximum is when, as a function of is when the potential is minimum. And in fact, the potential is less than it would be with no laser. Okay. So this is when, if I'm considering the electronic structure of the atom, if I have a laser beam which is red detuned, so the laser frequency is less than the atomic frequency, then the optical potential is going to be like the intensity of the laser beam divided by the detuning, and in this case, this detuning is is less than 0. Okay, so then the potential is less than 0, and it's an attractive interaction. So now, if I now look in the other direction where this lattice is made, I'm now not moving along Z, but along a perpendicular direction, but I'm still moving in the intensity profile of that laser beam, which has a finite extent. Okay, so these beams have a finite width, and if a particle goes from within their diameter to outside of it, you would have to increase energy. So that's rolling up a hill.
Okay, understand.
Yeah.
Thank you.
Okay. Good. Good.
Great.
Yeah.
Thank you.
Good question. the question has practical consequences because if you instead use a blue detuned beam to make the optical lattice, then you could be pushing atoms out. And in one of my labs, we do that, and we need to compensate with other laser beams. Good question. Okay. All right. All right, so other questions? All right, I now want to talk to you about a model for interactions in the lattice. And it's a model you may have seen before. How many of you have seen the Hubbard model? Okay, maybe half or so. Yeah, so what we've been talking about so far is a Hamiltonian that describes tunneling like this, where particles can move around. If there's a spin, I need to add a spin index to the creation and the annihilation operators. But what we haven't talked about yet is interactions. And so I want to talk about this. How do you figure out what the interaction is when two atoms are on a single lattice site? Okay. To see that they're there, we'd have to write a Hamiltonian which measures the presence of, let's say, a spin down and a spin up atom, or for bosons, the presence of multiple bosons. But let me first talk about how to calculate a U for two atoms on the same site, and then we'll come back to how to develop this second quantized form. Okay, so a pretty reasonable way to approximate U is to say that I have an on-site interaction strength, which is the integral over the positions of two particles times their interaction potential, which might depend on the distance between the two particles. And then I want to write down a wave function for each of those particles. But we know what that is already. It's the Wannier function for the lowest band, if we're looking at a single band model, for position 1, and the Wannier function for particle number 2. So what do we do with all these things? Well, an approximation we can make is we can call this approximately equal to this ground state harmonic oscillator function. Okay, so a simple harmonic oscillator wave function, and also this one too, except we're going to say that's particle 1, okay? And then for the interaction potential, which Fred Chevy told you a lot about last week, despite all of his warnings, I'm just going to say, well, what if we make this a delta function? No, don't do that. Yes, I'll just do that for a moment. Okay, so then what do we have? We then have that the interaction potential is some kind of coupling constant times the integral of the 4th power of the Wannier function. Okay, and I need to write out these harmonic oscillator functions in relative and center of mass coordinates to do this, but all right, I assume you can do that. And so now we just have some kind of relative coordinate to the 4th power d cubed r times some constants, okay? And what's nice about this harmonic oscillator approximation is you can do this. You can integrate the absolute value of Gaussian squared, and you can come up with a nice approximation. If you do that, you find that this U is equal to the following. Which is some other constants, square root of 8 over pi times k times as, and lattice depth to the 3/4 power. Okay, so what do I mean by k times as? I mean KL is just the same k lattice I've been using, but now this G, remember, is 4 pi h bar squared as over m. And this as is the S-wave scattering length. So let's see. Must bother you that this is a dimensionless number, so I think this is u in units of recoil. Yeah. Okay. So does this make sense to you? Well, think about what I had said earlier. If you had to guess about how strong an interaction would be, you would say it's probably going to go like the coupling constant times the density. The density here is 2 particles divided by a harmonic oscillator length cubed. And we just said that the harmonic oscillator length goes like 1 over lattice depth to the 1/4. So that means density should increase like lattice depth to the 3/4. And indeed, that's what we find. Okay. All right. So how strong is this? Well, it better be weak, because if it's really strong, my whole approach to the calculation is wrong. I'm assuming that each particle just has a wave function that looks like a single particle wave function, and that there's no strong correlations between the particles, like they don't avoid each other in order not to interact. And so this idea that I do a calculation with Wannier functions to the 4th power is necessarily a perturbative calculation. And that's why I can do this, kind of crude approximation with the delta function, et cetera. Let's see how weak or how strong these things are. And to do that, let's calculate some ratios. So I'm going to call these ratios gamma. So one of them is the on-site strength, which would be the ratio of interactions to the average energy of the band, okay? The average energy of the band. And the average energy of the band is basically just, h bar omega naught or so. That's what we have for the lowest band. Let me remind you why that's the case. Here, so the lowest band is always just equal to, especially when you get deeply bound, but even at the very beginning, it's already that the harmonic oscillator prediction for the energy and the actual energy is pretty close. So roughly, the lowest band always has 1 0 point of energy for a harmonic oscillator. And so the ratio we can calculate, we just said that the interaction, which is on the order of u, is ER times KLAS, and then it scales like the lattice depth to the 3/4 power, whereas the harmonic oscillator goes like recoils times lattice depth square rooted. Okay, so why is that? Let me just show you again. The harmonic oscillator energy goes like this, which is the same thing as 2ER times the square root of VL over ER, which is just S to the 1/2, right? Okay, so putting these things together, you see that a bunch of stuff cancels. I can cancel these factors out, and can cancel this and make this just 1/4. And so you find that this goes like this dimensionless parameter KLAS times lattice depth to the 1/4. Not that strong. So if I have a lattice depth that's 64, I can take the quarter root of 64, I think. No, I can't. 32, there we go. Then that, S to the 1/4 is 2, and I've just, even for a 30 recoil deep lattice, still have this KLAS parameter. And how big is that? KLAS. So KL is 2 pi over the lattice constant. What's a typical lattice constant in nanometers? Yeah, 500, let's say. Sure, few hundred, okay? And what's a typical scattering length? Yeah, so you might think it's something atomic, like a Bohr radius. It's actually about 100 Bohr radius because it's more like the van der Waals length. It comes from a length scale determined by the 1 over r to the 6th interaction of two atoms far away from each other. So this AS here, let's call it, you know, something like 5 nanometers or so. And so you see that this is really much less than 1. Even with a 2 pi, it's 2 pi over 100. And so KLAS for typical alkali, far from Feshbach resonances, is weakly interacting. And in a way, that's good news because it means I can do a perturbative calculation of the on-site energy. But in a way, it's bad news because if I go to your condensed matter colleagues and I say, I study weakly interacting atoms, or you go to your high energy physics colleagues or your nuclear physics colleagues and you say, I study weakly interacting atoms, then they say, that's boring, I'm going to take a nap. Of course, weakly interacting atoms are really interesting in many ways. If you want to do high precision measurement and measure the change of fundamental constants in the universe, okay, then someone might wake up, right? But if you want to study many-body interacting physics, you want things to interact strongly. Fortunately, this is not the right ratio to calculate to figure out whether lattice physics is interesting. What we want to know is a different ratio, which is the long-range ratio. Okay, and for that, I want to know the ratio of U, the same interaction, to T, the tunneling coefficient. Okay, so the tunneling coefficient has a nice approximation. I mentioned it, but I don't think I ever wrote it down. Let's write it down now. Which is an exponential. Oh yeah, so it's something like ER times S to the 3/4 times E to the minus 2S to the 1/2, okay? And you can see that in some ways, okay, yeah, so let's just calculate this ratio now. It's still ER KLAS times S to the 3/4 up top. But now on the bottom, I have S to the 3/4 times E to the minus 2S to the 1/2. And you see that's great because this is going to go like KLAS still, but times E to the plus 2S to the 1/2. Okay. So this ratio here is still small. It's still the same thing, which we said is, you know, roughly 2 pi over 100. But I can make this number really large, you know. So if I take a lattice depth that's 30 again, what I mentioned earlier, you know, then I have E to the 2 times, you know, square root of 30. Is that really what I wanted to do? Anyway. I guess 16 to the 1/4 is 2. Sorry about that. So anyway, then, you know, this is becoming exponentially large, like the square root in the couplings, square root in the lattice depth. Yeah. Yeah.
What do you mean by long range in this case?
Yes, yes. What I mean is the energies that are present in the Hubbard model. So let's go back to that. Yeah, so in this model here, the only competition for on-site interactions is this kinetic energy term here that comes from hopping. So if this is strongly correlated, it means that, well, let's start out. If it's weakly correlated, that means that the U is so small that it's a perturbation to the band structure we already calculated from this term. But now, in the flip case, if it's strongly interacting, so U is much larger than T, then the eigenstates are going to be approximately the eigenstates of this term, and then the kinetic energy will be a Hamiltonian, and that's what we mean, a perturbation, and that's what we mean by strongly interacting.
But why long range?
Because long range is the kind of kinetic energy I get from hopping from site to site to site. And so it's the kinetic energy that exists at the multi-lattice site scale, whereas the previous thing I was calculating was just this, just the 0-point energy here, and that's the kinetic energy I have oscillating back and forth on a single site. And that's a very short range scale.
Just one more question is,
good questions.
How can we make sense that by making the potential deeper, we have stronger interactions? We have like a greater effect of the interactions.
How can you make it, or how do you understand it? Sorry.
How to understand it?
Yeah, I guess it's two effects happening at once. One of them is that as I make the atoms denser on a single site, then the density goes up. As we said, that goes like s to the 1/4. But the other thing that's happening, which is more significant, is the tunneling is going down. Okay, so just to remind you, the tunneling is given to you by the width of any of these bands. And as I make the lattice depth stronger and stronger, then the kinetic energy is basically what's available in that bandwidth. So as this bandwidth gets smaller and smaller, and the interaction energy doesn't go up, it doesn't go down, it goes up as well, then the ratio between those two becomes large.
Thank you.
Yeah, good question. Other questions? Do you want a microphone?
Thank you. What type of orders can usually do with this parameter, with the U over T?
It can be kind of as large as you want, in that the lattice depth, we can realize in the lab is 1,000, so, that's e to the 60.
Okay.
But the issue is, the reason that's not actually useful is because in order to get to this really high ratio, I'm really getting there by reducing tunneling. And eventually, the time it takes for the system to equilibrate, just gets longer and longer. So the slower the dynamics, the longer you need to wait to see, let's say, a ground state of a system, or to study the non-equilibrium dynamics, because the timescales for dynamics and relaxation is all governed by tunneling. So once I turn up the lattice depth beyond something like 30 recoil, practically speaking, it means that I'm no longer doing multi-site physics. It's just too slow before other problems happen in the lab, like heating or loss, or my graduate students run out of patience and they turn off the experiment, So essentially, the U over T is only limited by the time scale of experiments slowing down.
Okay. And there's no lower limit?
No, and it can also be 0. That's right. We can turn off the lattice, and you can tune a Feshbach resonance to 0 crossings. So, yes.
Okay. Thank you.
Good question. Yeah. Okay. All right, so we've talked about how to calculate the interaction. Now let's talk about what kind of particle number is allowed on a single site. And for that, we need to think about quantum statistics. So what I mean by that is, if I have bosons, and I start with a vacuum, and I want to create a particle on, let's say, site J, then I can do that. And so then I make one particle on site J. And then I want to do it again. I want to start with this, and I want to move another particle to that site. I not only get this, but I get a bonus square root of 2. Okay? And I can keep going. So you can make any number of particles you want of bosons at a particular site. With fermions, things are a little bit different. And let me write the fermionic operator C. So if I want to make a single particle on what was an empty site, that's great. But now, if I want to make another particle on this previously occupied site, I get 0. So the reason that's the case is that fermionic operators obey an anti-commutation rule, which is that, for instance, Cj hat, let's say Ci hat, anti-commute like this. And if I write this out, it means that Cj Ci plus Ci Cj is equal to 0, all with hats, let's say, daggers. But now, in the case of looking at the same site, then this is just Cj Cj plus Cj Cj is equal to 0. Okay, and these are the same things, right? So once I go to the same site, it must be that applying this creation operator twice just gives you 0. Otherwise, you're not obeying the anti-commutation rules of the operators. So this is how you get to the Pauli exclusion principle. That you can't have two particles of the same quantum state occupy the same quantum states if they're fermions. Bosons, on the other hand, obey anti-commutation rules, and so there's no such restriction. Okay, if I go through the same math, it's fine. If I have two different bosonic operators, then they anti-commute, but that means there's a minus sign between them instead of a plus. Okay, so what that means is that when I write out Hubbard models, I need to think about different scenarios depending on different particle types. So for the Bose case, for bosons, I can write out the occupation of a single site as the number of particles on that site times the number minus 1 on that site. And then if I have 2 atoms on the site, then I have 2 times 2 minus 1, which is 2. So I can write this out as U over 2 times occupation minus 1. Whereas for fermions, I need to write this out a little differently. I can't really have just occupation on the same site for the same kind of particle. So if I live in a single band, instead, I'm going to think about an interaction term which is the occupation for a spin-up particle and the occupation of a spin-down particle on the same site. Or I need to go to multi-band problems where I put one fermion on the lowest band and one fermion that's identical on the next band. If I do that, though, they need to p-wave interact. And we're not talking about p-wave interactions here. So for s-wave interactions, you want this kind of interaction term for the Fermi-Hubbard model. And that's what I'm showing here. So this is a Fermi-Hubbard Hamiltonian. And if I wanted to do bosons, looks like this. Okay. I'll come to this other stuff later. But basically, local interactions for bosons have this n times n minus 1. Oh, and this should be a 1 over u over 2 here, by the way. Okay, Does that make sense? So just to recap, we've studied this a lot for single particle physics. That gives you block states, but you ruin the block states, perhaps, if you have an interaction. We can do a perturbative calculation of this on-site interaction, but still have strongly correlated physics when we're looking at the length scales of mini lattice sites, and now ask about the interplay between these two terms. In a sense, they fight each other, because the eigenstates of this are the block states. What do you think the eigenstates of this are? Were you talking about Fock states in this morning's lecture? In Marcelo's lecture? Yes? What is a Fock state? An eigenstate of the number operator. Yeah. Right, well, these are number operators here. So if I have a Fock state, then I've diagonalized this thing. I mean, I was just talking about number states when talking about what the interaction energy has to be. But if I try to put a number state into this Hamiltonian, what does it do? Yeah, and then what does that mean physically if it tunnels. Right, it's not an eigenstate. So this one tries to connect up all those number states and make them coherent, right? Whereas this lets them be and gives them an energy. And so now if I change the relative magnitude of t and u, then I go from one limit where I have delocalized states that have well-defined momentum to another limit where I have localized states, number states per lattice that only have well-defined occupation number. So this is like a coherent state, and this is like a Fock state basis. Okay, so you can observe this in the lab. Let's see, do I want to tell you about anything else before I show you that? No, why don't we just talk about that? So so here's an example of that kind of transition, where I have in this first picture here, sorry this isn't well labeled, this is just some data from a famous paper. So in this first picture there's no lattice on, and I just see a Bose condensate without being perturbed by the lattice, and a Bose condensate is very much like a coherent state in that, coherent state, in that it has a well-defined phase, but not a well-defined number. But now if I turn up the lattice, then this relationship between u and t changes, the one I was just talking about, and as u becomes more and more dominant, then we can't reasonably have this kind of eigenstate anymore, and instead we have these kind of eigenstates, but they don't have a well-defined phase. And so if I drop the particles out of the lattice, I just get mush instead of a nice diffraction pattern, because if I have incoherent matter waves, they don't diffract into nice peaks anymore. And so to convince people that this mush was something interesting, these authors here had to show that reversibly you could come back to that coherent state, but there really isn't a lot of information in this picture. What you want to do to measure the order parameter for this number state is actually measure the number, right? So to make a long story short, they measured the number. Instead of looking at things in time of flight, people built microscopes that could see individual atoms in the lattice. So here's some pictures from various groups. And now I can point to a particular lattice site and say, there's one atom there, and point to its neighbor and say there's 0 there. So we're measuring number states. If this is really nice, what you want to do is measure not just 0 and 1, but 0, 1, 2, 3. And you can kind of do that. The way you do that is, first of all, the lattice sits in a harmonic confining potential. So at the very edges, there's just 1 or 0 atom. And then further in, because the density is higher, you're kind of choosing between whether there's 1 or 2 atoms. And then further in, you're choosing between 2 or 3 atoms. Yeah?
Basically, if we sum all the contributions of the atom, basically we have like a Gaussian state.
In this case, I'm telling you about number states and how they're observed,
Okay.
not the coherent state. So the evidence of there being some kind of Gaussian distribution, this is, I think you're thinking about this kind of
Yeah,
state.
exactly.
The evidence for that is not that the atom number distribution is measured at a particular site, but rather that its phase is measured.
Oh, okay.
And remember, those coherent states are have a well-defined phase. I don't know if it was introduced to you that way, but they do. Okay. Yeah, so instead of measuring the distribution of number on site, these experiments in time of flight are sensitive to a phase. But in a trap, if I measure the atom number in a trap, then I'm trying to measure atom number, and what I'd like to do is see 1, 2, 3. The problem is that when I turn on these kind of microscopes, typically what happens is if there's 2 atoms in a single site, they photoassociate. So they make a molecule in an excited state, and then they leave the trap. Okay. So they do that pairwise, and what that means is if there's 1 atom around, I get to see it. If there's 2 atoms around, it turns into 0 atoms. And if there's 3 atoms around, it turns into 1 atom. And that leaves you a structure that looks like this. If things are ordered, then from the edge to the middle, there goes from kind of fuzz to 1 to 0 to 1 again, as I kind of go from the outside in this structure. And people see that kind of nice pattern when they look in situ. So in particular, what I've just described to you is this kind of donut pattern here, or this one. We're going from the outside. There were no atoms here. There's 1 atom there. And then there's 2 atoms per site here. It looks like nothing because they've pair projected down to 0. But the fact that it's nothing everywhere in a nice orderly way makes you think, oh yeah, maybe it was really 2. Not perfect, but beautiful nonetheless. And so let me just say that this data, actually taken by the same group 8 years later, is much more convincing than their time of flight measurement that you're seeing a number state. Because remember, the time of flight thing just looked like a schmutz, right? Whereas this here is really measuring the on-site number, especially between 0 and 1. Okay. So the last thing I want to tell you about then is this whole story again, but in momentum space. So far, we've talked about the Hubbard model written in terms of its Wannier states. Okay, I didn't really emphasize this, but when writing down this Hubbard model, we wrote minus t times these creation and annihilation operators. So creation at some site, annihilate at some other site, let's say, and then plus the interaction, and we had the number on a particular site. Let's say spin up and spin down. So what do I mean by these J's? All of these are the Wannier states. So these are the states that are well localized to a single position, and therefore are especially nice when talking about interactions, as we've just emphasized. But what if I go back to the block states again? The block states are the diagonal bases for this first term, and I would instead write them as the sum over all Q, and then just the number I have in the Q. That was the way we wrote down the Hamiltonian when finding the tunneling in the first place. So what does this next term look like, though? You know, we now need something proportional to interactions, but how do I write down interactions in momentum space? So to figure this out, we go through the same process we went through when we derived tunneling in the first place. What we're expecting here is that probably this one should change Q's to other Q's, just like this changed some sites to other sites, right? Whereas in this case, for the interaction, we had just number operators, so we could count the number of either localized states in this case, or we could count the number of momentum states here. The reason we expect some kind of change to occur is because we know the interaction energy is not diagonalizable in momentum space. It's diagonalizable in position space, so it must be somehow delocalized in momentum space. And so what do we do? Well, we know that there's a Fourier transform relation between these things. We know that, for instance, if I want to write down a creation of something at a particular place, then I can write it out as the sum with the correct phases of that location, and then create something at, oops, sorry, I'm not putting the right index. This is a CJ, right, there we go. So this is a creation operator for a Wannier state, whereas this is a creation operator for a block state. And so what we do now is we do the math of substituting in this kind of creation operator into here, but remember there's 4 of them now, because to write this out correctly here, I have a number operator, so this is, creation of and annihilation of a spin up, and then creation and annihilation of a spin down. I'll just say down, right? You also have to do something called normally ordering. How many of you have heard of normally ordering these things? Okay, great. If you don't understand, I can't explain it to you. It's just like religion, right? No. Okay, so this is what we need to do, and I do that math. It's here in the Dropbox, in my notes. Okay, what do we get? Let's talk conceptually about what we find. Yeah. What we get is basically atom-atom scattering. Okay. If I treat this thing perturbatively, it's maybe not so surprising that if I have block states and they can interact, and you want to change one momentum to another momentum, and you do that by encountering another block state, that's scattering, right? 2 different momenta come together, bang, 2 different momenta come out. What is conserved in a collision? We are considering elastic scattering, just elastic scattering, yes. So then what's conserved? Energy and momentum. What is momentum here? The problem is that all these Q states here that we're talking about, those are not eigenstates of momentum. They're eigenstates of quasi-momentum. Okay, is quasi-momentum a conserved thing? What do you think? Yes, the answer is it's conserved up to modulo 2 pi. Because if I scatter into the next Brillouin zone, so I go beyond pi, KL, then I've just told you everything is periodic in that parameter. The energy is periodic, for instance. So if I scatter into the next Brillouin zone, it's just like I stayed within the same Brillouin zone. And so I take the modulo 2 pi of the sum, and that's what's conserved. And it's really important. So this is the kind of interaction you get that if I write this and I go through the math I just described, you come out with 4 different quasi-menta, 2 in and 2 out. I guess these are the ins, these are the outs. And if I pick one of them, it has to add up to the others, modulo 2 pi, or if I'm writing this in units of momentum or wave number, 2 pi over AL. Okay. And so this is very much like an interaction vertex, except for that modulo 2 pi. And the modulo 2 pi is really important. If you do an experiment and you try to look at the damping of quasi-momentum or current in some way, those jumps to the next Brillouin zone do most of the damping, actually, do most of the scattering. So in a way I'm not going to describe to you, we set up some currents in a lattice, and then we change interactions or change density. And then we look at how quickly this thing damps out. And currents are damped by collisions, and we'll talk about that in a moment. And if we do a calculation which imposes strict conservation of quasi-momentum, as if it were momentum, and it were really conserved, then you get a little bit of damping, actually, but not a lot. This line looks almost like it's the axis, but it actually is a little bit of damping. But if I allow these so-called Umklapp scattering events, where I start within a certain QQ, and then I scatter modulo 2 pi enough to knock me into the next zone, you see I can understand the experiment and see the big damping. Yeah. Oh, I see, microphone. Yeah.
Sorry, but I didn't understand where this 2 pi came from. Can you explain it again?
Yeah, I didn't explain. Someone made an intuitive guess, and I said, yeah, you're right. Okay, so let me show you how the math works out. Maybe that'll help. Okay. It's a kind of like this. So if I have this Hubbard interaction term, which is a U times a creation and an annihilation operator. I'm going to get this a little larger. And for each of those, I take the Fourier transform. So I write each of them as the sum of the correctly phase-weighted creation or annihilation operators of a quasi-momentum state. And so when I add all this up, I end up with the sum of all those phases in the exponential here, okay? And as you probably know, when I sum up exponentials like this, I usually get delta functions. But this is a phase, okay? So the only thing I can really impose on e to the I something is that something is 0 modulo 2 pi, okay? So this conservation law that appears as a phase, more or less being 0, the math doesn't distinguish between the phase being 0 or the phase being 2 pi. And that's where this modulo comes from. Whereas when you're doing the equivalent thing in momentum space, you don't have the same periodicity of the problem, and so you don't have this 2 pi. Yeah. Yeah, great. Okay. Let's see. So I think the last thing I want to say is, how strange is it that collisions not only don't conserve quasi-momentum exactly, but also can damp current? So to talk about that, let me just bring you back to what we talked about last time. That let's see here. Okay. So I want to remind you that when I have energy versus quasi-momentum, and it looks like this kind of cosine thing, then we found there was a thing called group velocity. And the group velocity versus quasi-momentum was the derivative of the cosine, and it looked like this. Okay, so we found that group velocity was 1 over h bar, the derivative of the energy distribution with respect to q. And so the maxima and minimum here, if this band is, let's say, centered around 0 and goes up by 2t and down by 2t, then the group velocity order of magnitude is 2t over h bar, which is now a rate times al. Right? This has units of velocity. Okay, and so the picture is that if I have something that's sitting, let's say, here in quasi-momentum, then it's sitting here in group velocity, and so that's telling me that something with a positive quasi-momentum is also, moving along with a positive movement through the lattice. And the next thing I've just said is that if two particles collide, and so they have two different quasi-momenta, let's say there's something here and something here, total quasi-momentum is conserved, modulo 2 pi, but notice what can happen. Let's say one of these things moves up to here in its final state, and the other one moves down to here. Then in group velocity, something can move up to here and down to here. And one of these is a cosine and one of them is a sine, right? So if I'm conserving energy, let's conserve energy in these elastic collisions. And we're going to conserve quasi-momentum. Okay. In a collision, did we conserve current? With a collision? Well, what I mean is these two particles, they both have a velocity, and so together they have a mass current. They're moving, they're transporting mass. And then they collide. In free particles, you know that what happens, that the center of mass velocity is also conserved after a collision, because if total momentum is conserved in free particles, then total velocity is conserved. Those things are just related by a factor of mass. But in this case, group velocity and quasi-momentum are not related by a line with slope mass, right? So it's instead a sinusoidal relation between velocity and momentum. So now if I have a scattering event, even if it does conserve quasi-momentum, does it conserve group velocity? Yeah. Yeah, they might have something, there might be a different group velocity, because the current afterwards, so that the initial current is going to be, let's say, the velocity of particle 1 plus the velocity of particle 2, and that's going to be like the sine of Q1 plus the sine of Q2, whereas the final, etc., 3 plus 4, is equal to the sine of Q3 plus the sine of Q4. So even if these add up to the same value, and I conserve energy, which says that something like the cosine of Q1 plus cosine of Q2 is equal to cosine plus cosine, there's no reason for those two things to be the same anymore. So the collision in the lattice doesn't conserve current anymore, doesn't conserve the total velocity of all the particles. They have this funny relationship to momentum, which is not linear anymore. So what this is called, and the reason this occurs, is because you've broken Galilean invariance. So if I were in the center of mass frame, or the co-propagating frame with the initial group velocity, and I see the collision, I don't get the same final collision. Thank you. And so there's something really interesting about this, that once I choose a lattice, then it chooses a particular reference frame where the lattice is stationary. And if I have a collision, then I can't just do the thing I do in free space all the time in classical physics, whereas like, oh, I just go to the center of mass frame and I do the collision there. The center of mass velocity is 0 before and afterwards, and everything is simple, right? You can't do that unless every reference frame is the same. But once you have a lattice, you've chosen a particular frame, which is special, which is where these particles are moving at a certain velocity with respect to the lattice, which is stationary. So for that reason, collisions in a lattice don't conserve current, and it's very easy to have damping with collisions. So the answer to this is no. And you know, the kind of symmetry which is broken here is broken Galilean invariance. Yeah.
So can we say that we don't have more elastic collisions? Are they inelastic?
They're still elastic. They're elastic because I've required that they conserve energy.
Yeah. But
Yeah.
But to be elastic is just, I forgot. It's just conserving energy is the condition.
The
Don't need to
condition-
conserve momentum.
So
too?
even inelastic collisions conserve momentum.
Uh-huh.
You know, if two pieces of putty come together and they stick, then their total momentum is still going to be the sum of the two momenta. But the two things coming together that stick or deform don't conserve total energy. So the question is, for elastic and inelastic, is energy conserved? And in this case, yes, momentum's conserved because it is for all collisions, quasi-momentum here, modulo 2 pi. But let's forget about that for a moment. And then energy is conserved because it's elastic. no energy is transferred to the lattice, okay? But velocity is not conserved.
Okay. And how can we explain? For
Yeah, so the
Like,
reason velocity is not
where is
conserved,
it going?
I guess it only disturbs us because we've developed this intuition that's based on translational invariance, okay? We're like born and raised in Newtonian mechanics,
Yeah.
you know? It's kind of funny because it took physicists a long time to convince the rest of the world that a thing in motion tends to stay in motion. Like you say that to the Greeks and they said, no, not really. Right? But now that, you know, for centuries, Galileo and everyone has trained us that things in motion stay in motion. We believe Newton's first law. Now you're surprised when it doesn't happen.
Totally.
But, you know, if I move this, you know, it slows down. Things in motion don't necessarily stay in motion. So once there are collisions, the idea that collisions which conserve momentum also conserve velocity rely on Galilean invariance. Okay, rely on this idea that I can always go to the center of mass frame and describe the same physics. And when I have a reference frame which is special, then I can't. Yeah, so it seems strange, but it's life.
Wait.
Testing. Can I think of this as an analogous to the Drude model as collisions start to generate dissipation?
Well, the Drude model describes collisions of electrons with impurities in a metal. In this case, I have a perfect optical lattice. I haven't put in any impurities, and there's still damping. And that's because there's interactions between particles, which does not exist in the Drude model.
Okay.
So this is an interaction effect.
Okay, thank you.
Good question. Yeah.
I imagine that this isn't related with anything like relativistics, because when I saw like broken like Galilean symmetry before, it's like it always has to do with like relativistics effect. Like you have to do a Lorentz invariance in the other case.
That's not the case here. This is not a relativistic effect. Yeah.
How universal should be the interactions to this effect to hold? It's like what kind of interactions this?
Okay, so I've used a Hubbard model to define this kind of interaction, which is an on-site interaction, which is local in the Bonnier functions, and that means it's perfectly d-local for block states. All block states scatter with the same strength. And so just to remind you what that looks like, yeah, if you look at this model, for instance, Oh, because of the storm. Okay, yeah. Well, here we have an internet-proof thing, which is that the interaction Hamiltonian, when I write it out in quasi-momentum space, is the same U for all of the, you know, I had 1, 2, 3, 4, right? And two, like this. And it's the same U for all of them. And so it's a perfectly d-local or Q-independent. These were a sum over all the Q1, Q2, et cetera, Q3, Q4. All of these Qs had the same interaction. Now, if I have a more complicated interaction model, then I need to write some other terms here or something totally different. But it's still the case that there's no conservation law of current. So no matter what my interaction is,
cable.
it's probably going to mess up the current.
But usually we
This was in a sense my best
usually
chance
there
of
is
conserving
Wi-Fi,
it,
there is
and it
cable
failed. So
internet.
yeah.
But anyway.
And just another question. This is dealing or is related with the gauge symmetry breaking?
It's a good question that I don't know if I can answer well. I don't think it's the same symmetry, but I have to think about that. I'm not sure. There's one condition in which you do conserve current, which is when everything looks like a free particle in the end. So in this dispersion relation, if I have collisions between particles that are low in Q versus energy, so if this is, something where the dispersion relation is still parabolic, down here it's still the case that the group velocity is proportional to the quasi-momentum, and then if quasi-momentum is conserved, then group velocity is conserved, and you're okay again. It's only when you start to feel the non-parabolic nature of the dispersion relation in a lattice that you break this kind of linearity.
Thank you.
Oh, yes.
Can I just? I'm kind of like that is like how the math is done. Like, what do you transform and you see like this break of the Galilean invariance? Because I think it might be a different reference frame, see different group velocity, right? That's the and but how do you relate the current with that like? It seems to me like something related with the Nader's theorem. I don't know if that current is like associated with that kind of break symmetry, or like there is a more clear math that shows us.
So a Galilean transformation is to change your reference frame so that you're moving at a linear speed. Okay, so if I now have two particles that are colliding, then I could choose a frame where they have equal and opposite speeds. So I go to the frame in which the average velocity is 0, for instance, and that's what a Galilean shift could do for you. But since the dispersion relation that we've been looking at is, a sinusoid, when I go to that frame, it's not going to look like I shifted them down to 0 anymore, because the sinusoid is not a line, and so you can't subtract things off and get the same thing again. It's just a dispersion relation that's not linear, and you get the same phenomena in other nonlinear dispersion relations. Group velocity is not linear in momenta, also for waveguides of various kinds, for optics. So I've more than used up my time, a little past, so that's what I wanted to tell you. And if you want to read more about it, you can go to the notes that are posted, and I'm happy to answer questions later or over email if you can't find me here. Thank you.
Professor, could you write your email